All right, so let's look at the case of backward error analysis for linear systems. There are certain advantages to studying linear systems because, amongst other things, you can actually find a full-blown modified differential equation to all orders, if you will. And it's also a sort of a good exercise. It's like to illustrate what goes into the process of backward error analysis. Okay, so this is backward error analysis. For linear systems. Okay, so let's consider a linear differential equation. Okay, so dz dt is az. And the reason, as I said, is that this class of problems allow us to satisfy the condition that the one-step method applied to this sort of differential equation is equal to the exact time h flow of a modified vector field. Okay, so what that means is that you can actually compute these terms by terms. It's like the terms give you a series which converge. It's like, and everything sort of gives you something which is well defined. Okay. So this class allows you to satisfy this condition exactly, and allows us to demonstrate the basic ideas of backward error analysis. Okay. All right. So of course you know that if you have a linear differential equation, you know what the exact answer is, right? So the exact solution, of course, is nothing more than z of t is e to the at z0, and then your discretization, right? So you have a discretization. Let's say Zn plus 1 is equal to this numerical one-step method applied to Zn, which is in general some matrix, let's say B, which depends on H applied to Zn. And then so backward error analysis requires you to find AH tilde such that, right, Cn is equal to e to the Tn, AH tilde applied to Z0, right, and in particular, right, where Tn is of course just n times h, and then in particular, for n equals to 1, right, we have that the one-step method applied to Z0 is of course just BH Z0, which has to be e to the h a tilde h applied to Z0. So, so that allows you to solve for what AH tilde has to be, right? Maybe not too exciting, but yeah, it's easy to show what it has to be. So this implies that AH tilde is equal to just 1 over h, the natural log of BH, right? Of course, the same way that you defined the matrix exponential in terms of looking at the series expansion, for the exponential, you do the same thing for the natural log of a matrix, right? So where natural log of 1 plus m equals m minus m squared over 2 plus m cubed over 3 minus m to the 4 over 4, and so on. So note the following, right? If mu h is an eigenvalue of bh, then, right, lambda h tilde, which is 1 over h natural log of mu h, right, is an eigenvalue of ah tilde. And of course, this is nothing more than the relationship between eigenvalues of a map and its associated linear operator. Okay, so this is simply the relationship between the eigenvalues of a map and its associated linear operator. Okay, all right. So maybe it's like it would be helpful to look at an example of this. Okay. Okay, so let's look at explicit Euler. Right, so Zn plus 1 is equal to Zn plus h a Zn. So you want to write this as a linear operator acting on Zn. This is just the identity plus AH acting on Zn. So this is what I had called BH, basically. Okay, so let's consider the harmonic oscillator. Okay, so I'm essentially looking at a specific choice of the A. Okay, so you have Q dot is equal to omega Q, and P dot is equal to minus omega Q. So Z is Q and P, and then A is 0, omega minus omega 0. So you know that A has eigenvalues. Lambda plus minus, which are just plus minus I omega. All right, and then BH has eigenvalues. Let's call them mu h plus minus, which are 1 plus minus I omega, well, I omega h. Okay, so so I can write this as r e to the plus minus I omega tilde h. Okay, where r is equal to square root of 1 plus h omega squared, and then omega tilde, right, is equal to the arctan of omega h divided by h. And then if you look at the series expansion for this, it's like you can conclude that this is less than omega. Okay, so so what does that allow you to say, right? So the radius is increasing, right? Unlike with the harmonic oscillator, where it's like in phase space, it's like, you know, it's like the system doesn't, you know, it's like the orbit sort of doesn't grow. In the forward Euler discretization, the radius of this thing is growing, and then the frequency is slower. Okay, So basically the conclusion is that forward Euler is an expanding map whereas the exact flow of the harmonic oscillator is not expanding, right? Its eigenvalues are purely imaginary, so it's neither growing or decaying. But with the forward Euler, it's like method, it has this sort of growth factor. So I should say that's greater than 1, right? It's greater than 1. Right, and there is a phase shift because omega tilde is not equal to omega. Okay. All right. Okay, so let's just stop here for now. It's like, and then later we'll look at a more general sort of Runge-Kutta method applied to the harmonic oscillator. Okay.